established that optimization, adaptation, and learning over strongly connected networks by means of the distributed algorithms that we described in previous lectures is a stable, has a stable evolution. Whether you look at it from the mean square error perspective, or the fourth order error moment, or even the first order error moment, right? All of them we showed, they converge to bounded regions that are of the order of mu or of the order of mu squared, right? This was the main conclusion of the last two lectures. The analysis was a little bit demanding, but that's the nature of this problem because you have coupling among agents. So the problem becomes a little bit more challenging, but the main idea that repeated itself and which you are going to see again today is that if we introduce a particular similarity transformation, which you construct from the eigenvectors of the P matrix. The P matrix is the matrix that's related to the combination policies, right? If you introduce a similarity transformation that you construct from the eigenvectors of the combination matrix, that similarity transformation transforms the error recursion into a form that we can handle, right? Where you can reduce these conclusions from. Remember, this was one of the main arguments in the derivations, which you are going to see it repeated again today. Okay? So the argument repeats itself. So the material for today's lecture comes from chapter 10 in the text that you have listed over there, and which you can download from my website. Okay. So what we are going to do today, or start doing today, is the following. Now that I know that the network operates in a stable manner, what kind of performance can I expect from it? I know that the variance of the error tends to a region of size in the order of the step size. But can I be more explicit, right? Can I give an expression, for example, for the mean square deviation that we expect in steady state? We answered these questions for the single agent piece. We answered the same question for the centralized solution. How did we do it? We started from the error recursion, and then we developed a long-term model, right? We developed a model which we said, this is a good model for the evolution in steady state as I progresses to infinity. And the long-term model was such that I can evaluate its performance more directly. It's easier to evaluate the performance measure using the long-term model, right? And then we showed that the trajectory of the long-term model and the actual model were close to each other, so that from the MSD expression for the long-term model, I can deduce performance measures for the original model, right? Exactly the same strategy will be followed here. So in this lecture, I'm going to develop the long-term model for the network. And I'm going to show again that the trajectories of the original network and the long-term model, the error trajectories are very close to each other. And then I'm going to show you that this long-term model is also stable. Right? If you approximate the original network evolution by a model, you better have that this model also is equally stable from the first order error moment perspective, second order error moment, or fourth order error moment. So I'm going to show that. So today I'm going to motivate and derive the long-term model and establish that it is equally stable and show that its trajectory is close to the original model. And then next time, I'm going to come back and tell you, fine, now that I have this long-term model, let's use it to derive expressions for the performance of the network, right? So this is the plan of action that I would be following. Okay, we did this for the single agent case. I have to repeat it for the network case, with the understanding that, of course, the arguments are a little bit more involved because of the coupling, and you already saw examples of that. Okay, very good. So I introduced this assumption last time. When we introduce the long-term model, to motivate it, I need to assume that the cost functions are smooth enough, right, close to the Pareto solution. The omega star that you have here is the Pareto solution, if you remember, right? This is where the network goes to. This is what we showed in the last two lectures. So let's assume that the individual costs have Hessian matrices that are Lipschitz close to that solution. We introduced a similar condition last time. We introduced a similar condition also when we studied single agent adaptation and learning, and when we studied centralized adaptation and learning. Okay? So just remember that this condition is there, that the Hessian matrix is smooth enough, close to the optimal solution. And again, I showed you before that quadratic costs, logistic costs are examples of costs that satisfy this condition automatically, okay? So I'm going to use it whenever necessary. So what is the long-term model? First, let me remind you of the network model that we derived in the previous lectures. So again, remember that W tilde I is the vector that contains all the weight vectors, weight error vectors across the agents, right? And the letter E means each one of them is extended, right? That's all. Okay? So you understand the notation by now. So this recursion tells you how the weight error vector for the network evolves over time. Okay? So here you have the weight error vector. Here you have the gradient noise, again, collected from across the agents into this big vector S sub I. So when you don't have an agent subscript, it means this is the network quantity, okay? This is the bias vector. B contains the value of the gradient vectors at omega star, right? Again, extended. Okay. And the quantities that you see there, this is the matrix B, which determines the dynamics. It has the constant part that comes from the combination policies, and it has the random part defined in terms of this block diagonal matrix H, which is defined here in terms of the integral of the individual Hessian matrices. Remember, this is what we showed 2 lectures ago, that the network dynamics evolves over time according to this recursion. And in the previous lectures, we used this recursion to show that the network is indeed stable, right? Whether you look at it from a second order moment, fourth order moment, or first order moment perspective. Okay. Today, I would like to use this model and motivate a long-term model. So what would be the difference between the long-term model and this model? One of the inconveniences in this model is the following. What we would like to do now that we know that the network is stable, that we know that, for example, the variance of each error at each agent enters a small area of that size, right, in the limit, right? Then so as I goes to infinity, we know that. Okay. But now I want more. I want to find a good expression that tells me approximately how much is that to first order of mu, right? What is the coefficient that's multiplying that first order in mu, right? That's what I want to know. Okay, because I would like to find an expression that is first order in mu, some mu times something which I would like to know, plus higher order terms, little o, which I'm going to ignore, right? To do that, I need to introduce this long-term model. So how will the long-term model be different from this? What's inconvenient about model 2 is that the dynamics here, this B matrix is random, okay? And that makes the analysis, because when I want to evaluate this variance, if you square this term and take expectation, now you have 2 random quantities here multiplying each other, and you have to compute the expectation, right, of the square of the product of these 2 random quantities. That makes the analysis more challenging. The long-term model that I'm going to introduce is going to replace this B by a constant B, And then I'm going to show you that this long-term model, its evolution is close to the actual model. For that long-term model, using this recursion with a constant B, it will be easier for me to find its MSD expression, mean square deviation expression, which then I will transform to an expression for the original model. You understand the path I'm going to follow? Okay, that's why I'm interested in this long-term model. I want to replace this random B by a constant B, okay? So let's motivate that model. I did this analysis last time. I'm just reminding you. What we did last time, I introduced this constant block diagonal matrix. Here it is, right? In terms of the Hessian matrices evaluated at the Pareto solution. And so these are constant quantities. They are not random. And the difference, I called it H tilde, right? The difference here, I called it H tilde. So if I come back now to this recursion that you have here, okay, I'm going to replace this H by H tilde plus the constant H that I introduced, correct? Then this constant P with the part that comes from the constant H, that I'm going to call it this constant P. plus the rest, which is a term that depends on the random H tilde, correct? Okay, so if you do this, okay, if you do this, this is what you end up with. That this random matrix B is the constant B, right? Here it is now. Everything in this B is constant. And not only that, last time we showed that for small enough step sizes, this B is stable, right? And often we are using small enough step sizes, right? As small as we need them to be. So we not only know that this B is stable from last time, we also have an expression for its spectral radius, which is of the form 1 minus some term which is of the order of mu max. Here it is, the minimum eigenvalue of this positive definite matrix that you have here, which is the sum of the q's times the h's, right? And since these q's are of the order of mu, what I said here is correct, right? Okay, so we proved this last time. So now if I go to my error recursion and replace B by this, okay, this is the B, and then this is the additional term that will appear. Here it is, okay? I just call H tilde A1 W tilde, I called it C. You understand where this came from, right? Okay? I'm just calling that, this term here, calling it C. Okay, so this is what, we did this last time. You saw this last time, okay? Something similar to this. So now let's assess the size of this component here, okay? Which we also did last time, okay? But I'm going to remind you. So that C component, it's known on average is small. I'm going to show it to you, okay? How do you see that? Here it is. The norm of C, what is C? It's H tilde times A times W tilde, right? So the norm of C would be the norm of this times the norm of this times the norm of that, less than or equal, right? Okay? Then it is less than or equal the product of the norms. And then under expectation, so the expectation is only applied to the random quantities, right? Okay. But if you remember last time, I'm not repeating it here, but last time I proved to you that the norm, this norm here of H tilde is bounded by the norm of W tilde. This was one of the conclusions from the last lecture, okay? I showed this to you last time. Why is that? If you want to understand it very quickly, what is this H tilde? It's H minus the random H. Just follow the intuition. H minus the random H. The random H is an integral. Each one of the terms in the random H is an integral, right? Here it is. Each of the terms is an integral. The constant H, I can also write it as an integral, right? So you end up with an integral of a difference, right? So the norm of that, if you go back to this condition here, the integral of the norm of that will be bounded by a term which depends on the difference of the arguments, and that argument will be W tilde. This is what I did last time, okay? So if you didn't follow this argument, just go back to the notes and you will see it, okay? So last time we showed that this is of that order, up to some multiplying constants. We don't really care about these constants. The important thing is that inside here, you get a quantity which depends on the second order error moment, which we already know from the previous lectures, is of the order of mu, correct? So this confirms what I just told you here, that on average, the norm of this C is small, okay, of the order of mu. Fine, so far? Okay, very good. Now, since on average, the norm of C is small, this is what I'm going to do, okay? So this suggests to me that I can ignore this term and work with the remaining recursion. Okay? Of course, I'm going to throw away this term, but I'm going to examine explicitly what the implication of that is, okay, and how much error I introduce by ignoring it, okay? But at least the argument so far is telling me that on average, this term is small. Remember, this C on average is of the order of mu, but there is another mu multiplying it, which is m, right? Okay, so that effect is compounded. So this is telling me that this term here, on average, is of the order of mu squared. Okay? So this motivates me to introduce the long error, the long-term error model. And why do I call it long-term? I call it long-term because you see this bound here is in the limit, right? Yes.
When did you say on average is on the order of mu squared? Isn't it on the order of mu squared always?
No, because you see here, I'm showing here that on average, right, on average, the norm of C is mu, right? Okay. Whereas here you have C itself. Okay. So on average, that term is of the order of mu squared. Okay. So I'm going to use this argument to say I'm going to throw this away and continue with this part of the equation. And I'm going to call that my long-term error model. Okay? But I'm not going to do it just blindly. I'm going to analyze what's the effect of throwing away that term. Okay? Now, why do I call it the long-term model? I call it the long-term model because this is a small in the limit, right? In the limit. So that's why this is a long-term model. If I let my algorithm progress, we know from the previous two lectures that this term here, on average, is going to become very small. Okay, so let's throw it away. If I throw it away, I end up with this recursion. And you see, I use this notation here to indicate that I mean that this recursion holds for large enough I. Fine. Okay. Now, I continue to use the same notation for now, but if you run this recursion, these arrow vectors will actually be different, right? Because this recursion is different from the one that has the driving term involving the C. So actually, technically, here I should call these different names, right? Okay, different names. And that's what I'm going to do just to make sure that the notation is clear. Okay, so here it is. So this is just repeating what I just said, why I ignored that term. Okay. So this is the notation that I'm going to be using for the long-term model. I call it a state vector. So this is a state recursion, right? The new state is the old state times the dynamic times the matrix P plus some driving terms. So I'm going to use the prime notation for the long-term model. And without the prime is the original network, right? Okay. Now observe that the gradient noise term still is based on the state of the original model. Because this gradient noise is just a process. Think of it as just a process, like some signal that was generated. And this is the signal that I'm feeding into the long-term model. Fine? Okay? Very good. Okay. So here it is. This is the conclusion of this first part of the discussion, that I call this model a long-term approximation for the evolution of the network element. Fine? Of course, you can choose whatever model you want. Next, I have to show that it makes sense to use this model, right? Okay. I motivated it intuitively by telling you that the term that I throw away is very small, the order of mu squared, but I'm going to make that more precise. Okay? Now, later, in the next lecture, I'll come back to this model and use it to find expressions for the mean square deviation of the network, performance expressions for the network in steady state, because now this is an easier model to work with. You see you have a constant matrix here, a constant matrix here, a constant driving term there, so it will become easier for me to evaluate the mean square deviation, okay? But this is for next time. So this is a summary, right? So the B that you have there, this is the B. It depends on H. I'm just reminding you what the calligraphic A's are, the extended A's. M is the step size matrix. H is the diagonal matrix, block diagonal matrix, which contains the Hessian matrices, right, at the Pareto solution. Fine? Very good. So now we know what the long-term model is. And here I'm just reminding you that remember that this notation, what it means, right, it's a block vector. Right? It's a block vector consisting of one vector for each agent, right? And each one of these, in the general complex case, is extended in this manner. You have the vector and the conjugate transpose of that vector. I'm just reminding you that the structure is exactly the same as the original network, right? I'm just using the prime notation. Okay. Very good. Now, one thing I would like to mention here, which is useful for the analysis, is if you come back to this recursion, remember that I have a similar recursion, right, for the network. Okay. Now, if both recursions, I start them from the same initial condition, W tilde at 0 here is 0, let's say W tilde at 0 here, the prime is 0. Choose the same initial condition, and because they are both fed by the same gradient noise process, right? So the evolution of the error vector that you get from here, right, that you get from here, will also lie in the same space. You can express it as a combination of the weight error vectors that you get from the original system. Okay? Because this error here, when you run it, right, when you run this error, it will involve combinations of previous weights here and the same gradient noise process, right? So what I'm trying to say is that the error that you get from this long-term model will belong to the same, okay? It will continue to belong to the same filtration, which is the same space defined by the all past error vectors generated by the network, okay? If you start on the same initial condition and use the same gradient noise process, okay? So you can think of this error as belonging to that same space. This is just a technical detail, okay? Let's continue. Very good. So now what I'm explaining in these slides is the reason why I introduced the long-term error model is because now I replaced the random B by a constant B. I'm going to derive an expression for the mean square deviation of this long-term model, right? And then I'm going to show in this lecture that the trajectories of both models are close to each other by an amount that I can specify. Then in the next lecture, once I find the MSD, I add this correction term to it, I get the MSD for the original method. Just like what we did for the single agent case, right? I'm following the same approach. So now, let's study this question, okay? Very good. Okay. So now, this is the long-term model that we introduced, okay? And the first equation is the evolution of the error for the original network. Now I want to show that these two trajectories are close to each other, okay? Are close to each other, at least in the limit. That's what's important, because for performance analysis, I would like to know how well the network is performing in the limit, if you give it enough time to learn, okay? Very good. So now, if you were to do this, what would you do? If you were to evaluate how close this vector is to that vector, what would you do? You would look at the difference, right? If I subtract these two equations from each other, right, there are two big terms here that disappear. This term cancels out, and that term cancels out, right? And, okay, which would be used in the derivation, right? So, two terms cancel out, and I just have to worry about the difference of the first two terms. Okay? So this is what I'm going to show next. Okay? This is what I'm going to show next. And this is exactly the same result we showed for the single agent case. Okay? So there is a parallel. When you read these notes, you will notice, and that's done on purpose, the results that I have in the network case, almost all of them, not all of them, but almost all of them, parallel what we have for the single agent case, so that you can compare. Okay? Obviously, in the network case, there are additional facts that I need to prove. Okay? So this is what I'm going to show. Okay? So I have a network of n agents with a strongly connected matrix P. Okay? And then with the usual assumptions on the costs, the aggregate cost is strongly convex. At least one of the individual costs is strongly convex. The Hessian matrices of the individual costs are smooth, meaning Lipschitz in the manner I described. So these are the usual assumptions that we have, right? Under these assumptions, I'm going to show that the difference between the trajectories of the original network and the model, right? The second order moment that you see here is small. It's of the order of mu squared. And I'm also going to show that the variance for the original model, the second order moment there, which I refer to as variance, just okay, for simplicity, the variance of the network is related to the variance of the long-term model by this much. That's the difference. This is higher order power of mu, right? This number is smaller than mu because mu is very small, so mu to the 1/2 is smaller, right? So in the next lecture, we are going to derive an expression for this, just because the evolution for this model is simpler to handle. Then I'm going to take that expression, add this term to it, and that will give me an expression for what I want, right? This is what we are going to do next time. Today, I'm going to establish that this is the case, okay? That this is the case. Okay? So let's look at the proof, okay? So let's look at the difference, like I said. Okay, let's look at the difference. And then when you subtract, let's go back, like I said, if you subtract, what will you get? You will get the boldface B minus times W tilde minus the constant B times W tilde prime. But remember that the boldface B, right, the random B is the constant B minus, right, minus what? Minus, I believe, A2 transpose and H tilde, right? Something like that. H tilde, and then, okay, let me see if I have it written somewhere here. C plus. Okay, let me look at the expression just so that we get it right. Where is that?
A1
Here it is. A1 transpose W tilde, right? A1 transpose W tilde. Okay, so let's go back there. A1 transpose. So A1 transpose W tilde, right?
without W. Yeah, the
Oh, sorry, without W.
yeah, it's plus. Yeah, that's plus sign.
Plus. Okay. So now this quantity here, I will not. Okay, so you will get. You see, this times that minus this times that. It will include a constant B times this minus that. So I can group these two terms together. Plus the additional term, which will be this times now the W tilde, right? And this part I called it C, right? The last three terms. So that's why here you get this expression, right? So the difference is evolving according to this dynamics, okay? According to this dynamics, okay? Very good. And this matrix B is already stable, and we know that from the last lecture that its spectral radius is 1 minus something of the order of mu, right? Like this. Fine. Very good. So what do I want to show? I want to show that, for example, one of the results is this. I want to show that this in the limit, as I goes to infinity, the lim sup of that is of the order of mu squared, correct? Because that's exactly what the lemma says here. You see, this difference is z. So I want to show that the variance of z, essentially, right, is of that order. Okay? But you see, we have seen recursions like this many times so far. Okay? Whenever we study the stability of the network, we ended up with recursions that look somehow like this. Okay? So we already know how to do that. Okay? So let's do it again. Of course, I will move quickly through it. I will not show you all the steps because they are repetitive. Okay? The theme, like I mentioned earlier, is always the same. You introduce a similarity transformation using the eigenvectors of the P matrix, the combination matrix, that transforms your recursion into a form that is easier to handle, and from that form you get to conclusions, right? These are the steps. So what was the similarity transformation? I introduced the the Jordan decomposition of P, right? So the V is the matrix of eigenvectors. This J sub E has eigenvalues all inside the unit circle, and you have a single eigenvalue at 1 because your network is strongly connected by assumption, right? Very good. And then next, what do we do? Okay, this is the Jordan decomposition for the extended V, right? For the extended V. And then you can express your V, right, in this form, where in between here you subtract J from a matrix D, and this is the definition of V. Remember, we did this many times. Do you have any questions about this part to understand this step? Yes?
Professor, we can also use Cayley-Hamilton theorem to, the way we use it to solve this kind of recursion. To find out power of the maximum power of B and then express B to the power m in terms of the lower powers of b, and
But
then
that's a different problem, right? That's a different problem over there, right? Over there, you had a recursion, right? This is here is a true recursion. Over there, it was not a true recursion, right? In 210A, you're referring to the energy relation that we had there. It was not a true recursion, and I had to expand it. Bailey Hamilton helped us unwind it and transform it into a recursion. Here, I already have a recursion, right? 32 is a recursion. You go from gamma minus 1 to gamma. Okay? So, if I introduce, okay, anyway, so what you have on this slide, we did it many times, right? So I'm just reminding you, okay? So I can call this, for example, calligraphic V transpose. This would be calligraphic V, the inverse of that, right? Okay, so if you bring this to this side, right, you find that V is similar to this matrix in the middle, right? We did this many times. And the entries of these quantities D here, they are all of the order of mu max, right? All of them. Right? These are the expressions, but we don't need the expressions. Here it is, they are all of the order of mu max, and this one has spectral radius 1 minus of the order of mu max. We saw this many times, okay? So this is, I'm just rewriting it more compactly in terms of the extended matrix V sub E, which you take to the other side. So this is telling you that V is similar. We did this many times, right? I'm just reminding you. So it's always the same transformation. Once you see this, the first time probably, right, you probably found that this is, how did you think of this? But now that you see it and why it's important, it becomes part of the process. Okay? The key advantage of performing this transformation is that it allows you to represent V as similar to a matrix where the corner matrix is stable, right? The off-diagonal matrix are of the order of mu, right? And this lower diagonal matrix here has stable eigenvalues minus something of the order of mu, right? So this similarity transformation brings up that structure in V, right? If you just look at V, it's difficult to see. But if you look at this transformed version of V, you have this structure which we have exploited to great extent in the previous two lectures and today as well. Okay? Very good. So now if you apply the similarity transformation to the recursion that we had before, right, plus A2 transpose M C. So what do you do? Apply that transformation, right? Apply the transformation. Multiply by V transpose here, V transpose here, put V inverse here, right? V inverse and then V again, correct? You get, so this is, this quantity here is V transpose Z, which, right, you always partition the top part Z bar, the bottom part Z check, right? This has been our standard. So you see the arguments are repetitive, they repeat themselves, and that's good so that at least you get used to it. So this now becomes the matrix, which I'm calling V bar, and this is the driving term. Okay. What do we want to do? We would like to find, remember, we would like to bound this quantity in the limit, right? This quantity in the limit is related to the norm of this quantity here squared in the limit, right? Correct? Because you see, this, for example, here, if you call this transformation here, call it x, for example, just so that you see, okay? So you can see here that the expected value of z squared is what? Is, let's say, the expected value of the inverse x, right? Correct? So this, the norm of this, of course, this is upper bounded, you can upper bound because the norm of this, you can take it out. This is the argument that we usually do, right? So you can relate the norm of this to the norm of x squared. The norm of x squared, I can get it by adding the norm of z bar squared to the norm of z check squared. So that's why we focus on studying, right, the variance of z bar and the variance of z check, and we add them together, right? This is what we did multiple multiple times, right? Because the norm of this product here is less than or equal to the product of the norms, right? V epsilon has a constant, some constant, okay? So this norm is bounded by that norm, and if we show that this goes to something of the order of mu, you conclude that that goes to something of the order of mu, right? This has always been our argument, right? Okay? So now if you come back to this recursion, okay, so we are interested in evaluating this, and we are interested in evaluating this, right, in the limit. How did we do it before? If this is the recursion, okay, you see, you take the first equation, z bar is okay, z bar, I have to talk to the microphone, okay, z bar is this times z bar, and d21 times z check, okay, plus that. Well, if you want this part here, I can also divide it into an upper part, c bar, the lower part. You can always do that. You can partition. Okay. So I can write a recursion for z bar, I can write a recursion for z check. Of course, they will be coupled, right? And then I can square here. The square of z bar will be the square of this, right? And then you can apply Jensen's inequality to bound it, like we did before. And the same thing for z check, the same arguments we did before. Are you following what I'm saying? Right? So here it is. Okay, so I'm just telling you that the z bar you see here and z check, they are partitioned version of this, and then I partition that again. Okay. So this is the recursion. And now what do I want to do? You can write z bar is this times this z bar plus this times that z check plus z bar. And then norm squared, apply Jensen's inequality and proceed with the arguments, right? Are you okay with this argument? Okay. And of course we know, okay, we know how big these terms are, because I just showed earlier in the lecture today that the norm of C is of the order of the norm of W tilde squared. In an earlier slide, that's what I showed you. The norm of C is the norm of W tilde squared, because you get norm of H tilde times norm of W tilde. Okay? So therefore, C squared will be of the order of that, right? And then you have a mu here, you have a mu here squared, right?
But that was an expectation, right?
Yeah, without the expectation, you get the W tilde squared. With the expectation, you replace the W tilde squared by mu. That's why I said there, this term on average is mu squared. Here, I'm without expectation, but still, I'm keeping W tilde, right? You understand? What I'm trying to say is that these two terms here, because of this relation, we can relate them to W tilde squared and W tilde to the 4, which from the previous lecture, we know how to bound them by mu, right? Okay. So here it is. So the C bar will be bounded by mu, and the C check will also be bounded by mu, okay? Because if C itself is bounded by this norm, right, the C bar and the C check also will be bounded by, for some constants, right? So this is what I'm saying here, is if you repeat the arguments we did before, you will get something like this, applying Jensen's inequality. So here, I'm showing you what you will get, right? I'm not going, remember, you put 1 over t times t, 1 minus t over 1 minus t, and then you get the t, right? That argument, Jensen's argument, here it is, okay? So you get this recursion involving z bar, z check, and W tilde to the 4, and then you get something similar for the z check quantity, something similar, okay? Exactly the same arguments we did in the last lecture and the lecture before, okay? It's the same argument. Rather than carry these quantities with me, I call them A, B, C, D, E, F, G, right? Okay. Okay. You always laugh when I get to this slide, but okay. You understand? But what's important, I don't really care about the exact expressions for these quantities. What's important is what order they are, that's all. You understand? That's what's important for us. What is the order of these quantities, okay? So, when all is said and done, we get the recursion that we usually get. This is the recursion. Exactly similar to the recursions we got before. right? When we were studying the expected value of W tilde squared or the expected value of W tilde to the 4, here we are studying the expected value of Z bar and Z check squared. Similar recursion, and I know the order of each one of these quantities that appear here in steady state. This one is mu squared from the last lecture, E and F from the expressions I showed you, and A, B, C, D from the expressions I showed you. I know exactly what they are, right? So if you compute I minus gamma inverse, right, take the limit now of I minus gamma inverse times this as I goes to infinity, right? You will find, okay, you will find that these quantities here will be of this order and that order. Fine. Simple algebra, okay? And therefore Zi, which is related to Z bar squared and plus Z check squared up to some constant, will be on the order of mu squared, which is the largest of both, right? But remember that Z was exactly the difference. So we proved our result. Correct? Right? So you see, it's the same argument that we always follow, okay? Applied here to this recursion, okay? Very good. So I proved that the trajectories, the difference between the trajectories is like that. There is one more element in the proof, if you remember, okay? I wanted to show also that the MSB for the true model, I mean, as I goes to infinity, the lim sup of this, right? The lim sup of this is upper bounded by the lim sup for the long-term model plus some correction term, right? Which I want to show is of that order. Right? So this is the argument to show that. How? I did this argument before. So this is the error for the long-term model. Just add and subtract the original error. Nothing changed, right? Okay, nothing changed. Well, you can expand that square quantity. Okay, so this is the square of the first term, the square of the second term, and this is the cross product between both. Obviously, if I'm using the magnitude there, it becomes less than or equal here, correct? Okay, less than or equal. Then here you can use Cauchy-Schwarz because this is like the inner product between two vectors, right? The inner product between two vectors, right? You can bound it by the product of the norms, right? Here I'm using the norm squared, so you have the square root. But what's important from all of this is, you see, I would like to find how far this is from that in the limit. Well, how much is this? I just showed this is mu squared, right? Mu max is squared. Here, also mu max is squared, right? And what about this? Mu max from previous lectures. So here you have mu max cubed. The square root makes it 3/2. That term dominates this term. Mu to the 3/2 is larger than mu squared, right? That's where you get that the difference, right? The difference is like that. Correct? So we proved the lemma. Okay, so I introduced a long-term model, and now I justify that actually in the limit, if you let both models run, and I'm going to be showing you in the next slides that the long-term model is indeed stable. The network is stable. The long-term model is stable, whether you look from first order, second order, or fourth order error moment. Okay, so now if I let them run in the limit, their trajectories will satisfy these bounds that I showed you. They will be close to each other. Fine. Okay, so I proved that first claim. Okay. Fine. So now I prove the second part, which is that the long-term model I introduced is also stable. So all the three properties I proved for the network, I'm going to prove them for the long-term model. But again, I'm not going to repeat the arguments because similar to what I just did, similar arguments will come up again. Simple, a little bit simpler because now I only have a constant B. In the previous two lectures, I always had the standard B there because I was studying the network. Okay, but the arguments are similar. You introduce a similarity transformation, you introduce these D matrices, you have this vector evolving according to this recursion, apply Jensen's inequality, and then get the final recursion, take the limit. This argument repeats itself, okay? So let's first establish the second order stability, which is this. Right? The prime is used for the long-term model. If you let the long-term recursion run, the second order moment of its error at every agent will also be of the order of mu, just like the network, right? And then we're going to show later that the fourth order moment will be mu squared, and we're going to show later that the first order moment will be only mu, right? All three versions that we proved before for the network, we're going to prove it here. Okay, so let's first prove second order stability, right, which is this statement that you have here. Okay? Proof. Okay. Remember that we have a recursion. What's the recursion for the long-term model? Just like this, right? Plus a driving term plus, I think it was something like this, A2 plus A2, right? B, correct? This is the recursion for the long-term model. I throw away the C term, the last term, right? Okay. I want to evaluate the variance of this, right? Because if I can show the variance of this is of the order of mu, the variance of each term in it is of the order of mu, right? Again, so what do you do? By now you probably know the process, right? Let's first transform it, right? Use a similarity transformation. What similarity transformation? The one you get from the eigenvectors of the P matrix, right? So by now you know it. So here, I already wrote it down, right? I already assumed that you already multiplied this from the left by V epsilon transpose, right? And call it W check W bar. Okay, this will be V bar. You see here you have that, and here you will get, because of the definition of the W star, the first entry here will be 0, right? As usual. Okay. And we also know how to bound the variance of this, right? Because by assumption, each error, each gradient noise term in this vector S has a variance that's bounded, right, by W to the square or W to the fourth if you are doing fourth order moment study, right? Okay, so each one of these terms, just like we did before, this term we can also bound it by a quantity that depends on W to the squared, right? Okay, so technically, from this point you can proceed, just like before. Okay, you understand? And establish the quantity establish the result I just showed you. Okay, so here technically you can proceed exactly similarly to what we did before. Okay, so here it is. I'm just telling you what this Z is, right? I multiplied by Vx. Okay, very good. Now I'm going to do it slightly differently here, just to show you another argument which is actually useful in this case. Okay, useful in this case. Because I have this 0 up here, okay? I'm going to introduce two recursions, okay? This recursion here does not have the gradient noise component. So this recursion is purely deterministic, fine? Assume I introduce this recursion. You will see very soon how these recursions relate to what I have, okay? So this recursion is deterministic. The second recursion, okay, the second recursion has the noise component in it. Okay, so let's go back. You see here, you have the noise. What I'm doing is this. You have the noise component, right? So I'm introducing two recursions. One is this. Let's write it here. One is A. This matrix B bar times A plus this constant driving term. Okay? And the other is random. So this B here is bold phase random is the same B bar, okay, plus V transpose A2 transpose M SIE. So what happens here? I split the recursion into two recursions. One is purely deterministic, the other is contains the random contribution. Because you see, if I subtract, did I use plus here or minus? I think it was plus. Plus. You see, observe that if I subtract at any time B minus, if I compute B minus A, you see, BI minus AI is ZI, right? B bar, BI minus 1 minus AI minus 1 is ZI minus 1, plus this minus that. You get the same recursion, correct? Okay? So if I can show that these two are bounded or divariant, because I can relate the norm of Z, of course, to the norms of B and A. I can also relate the norm of Z squared to the norms of B and A using Jensen's inequality, right? To the norm, to the variances of B and A using Jensen's inequality. Because the norm of Z squared is upper bounded by 2 times the norm of B squared plus 2 times the norm of A squared, right? Something like that. So if I can show that A and B, their variances, A in this case is deterministic, it doesn't have a value, it's just the norm of A squared, and the expected value of the norm of B squared. If I can show that these are of the order of mu squared, right, or mu, that's what I mean, then I conclude that the variance of this is of the order of mu. You understand what I'm doing here? Just a slightly different argument. Why I did this? Because I want to remove the deterministic term from the stochastic recursion. Okay? It just makes the argument a little bit easier. So let's look at that. For the deterministic equation, look at the deterministic equation. You have a recursion like this. This is a stable A, and this is a constant term, right? Constant. So where does this go to? Converges to I minus B inverse times that constant term, right? It converges exactly to that value. But what's important to us is last time, and I told you we are going to see this last time, this I minus B bar inverse matrix, I don't really need to know exactly what the entries are, but I know its entries are of that order. 1 over mu, 1, 1, 1. And this quantity here is of the order of 0 mu, right? So when you multiply this matrix by that, what are you going to get? Okay, so I minus B inverse times this. In the first row, we are going to get something of the order of mu, and in the second row, something also of the order of mu, right? So you can see that, I know right away that A is of the order of mu, correct? So A squared is of the order of mu squared. But I want to show that the variance of Z is of the order of mu. So it's actually B that will determine that, it's not A, okay? So A has a small contribution, it's mu squared. So let's look at B. Okay. Now B is exactly similar to the recursions we studied before, okay? I threw away the constant term, that's what I did, okay? With this argument. B, right? So I have a recursion for B now, you see? B, and then I think you had something like this, and S, right? This is exactly similar to the recursions we had before, okay? Apply the similarity transformation. You split it into B bar and B check. Find the variance recursion for B bar, the variance recursion for D check. You will, right? You will get it. Okay, here it is. You see, I already transformed, right? I already multiplied from the left by V epsilon T, right? Here it is. I call it B bar B check, S bar S check. And these two, I can bound them by the norm of W to the square by assumption, right? Remember, we have assumptions on the gradient noise that they are bounded by some constant times W to the square plus some other constant. Remember that? Okay. So when you do this calculation using Jensen's inequality, exactly the same argument, right? Exactly the same argument again. Because it is the same matrices here, right? The same matrices. You will get recursions that look like this. Where did these terms come from? From the bounds on the gradient noise. right? Because they are bounded by W to the square, right? And these are W bar and W check just because they are transformed version under VE. Okay. So if you do that, you are going to get the same ABCD here, whose order we know what it is. You are going to get this quantity H, whose order we know what it is. W bar and W check, we showed before that they are of this order. And this driving term is of that order. So if you take the limit now, I minus gamma inverse times this, in the limit, you are going to find that B bar goes to the order of mu, B check goes to the order of mu squared, therefore B itself goes to the order of mu. Okay? So B goes to that order, and like I said before, Z squared is bounded by that. This is mu squared, this is mu, so you get mu. Right? You see the same argument repeats itself. Okay, by now you got used to it. Okay. So we proved that the long-term model is the second order stable. Very good. And then the same thing will happen now for fourth order and first order. Okay. Yes.
The analysis that we did for the deterministic term here.
Yes.
Why couldn't we apply it for the random term also? Like I minus B inverse times the random term and take the expectation.
Yeah, well, you have first to find the variance recursion here, right? Yeah. You have to find the variance. First, you have to find the recursions for the variance. Because you are interested in the limit of the variance, right? Okay. So here, to find the variance, these recursions are coupled, right? Are coupled. So that's why you are going to get a recursion that now looks like this. So first, you have to transform it into this form. Then we take the limit. We take the inverse, right? Because we are interested in the variance. Because these are random quantities here, right? These are random quantities. We're interested in where the variance goes to, right? You are saying take I minus B inverse times that, then you're saying this random quantity is going to that random quantity. That's not what we are interested in. We are interested in where the variance is going to. Okay? That's the kind of calculation we have to do. Okay?
Can't we take the norm square of both the sides once we have that?
Yeah, but that's what we did, right? That's exactly what you are doing when you do this argument. Okay? That's what we are doing. In the limit. In the limit. Okay. Now. Again, I'm not going to go through the detailed tools, you understand it, right? So this is the argument. Okay, you find the recursion here, right? And then for B check, then you introduce the A, B, C, D's, right? And you write it in that form, and then from this you take the limit and you get what you do. Okay? So let's go to the fourth order stability. So with these arguments, you'll end up at least getting a good idea of what the previous arguments meant, now that you're seeing them again. Okay, for the fourth order case, now I want to show similarly, the fourth order moment is of the order of mu squared, right? For the long-term moment, the argument is similar, okay? The argument is similar. Let's look at it quickly. The recursions are here, right? I took the error recursion for the long-term model, transformed it, and then I replaced it by these two equivalent recursions in this case, just because I wanted to separate the deterministic part from the random part, okay? This one, you already know where it goes to, right? A goes to the order of mu, so A to the fourth goes to the order of mu to the fourth, because now I'm interested in the fourth order moment, okay? This is the same recursion for the B and B check. Fine. So now I'm interested in the fourth order moment of this, right? Again, apply Jensen's inequality to this recursion, right? Take B bar. First of all, write what B bar is. This times that plus this. Take the fourth order moment of that. Apply Jensen's inequality. You'll end up getting an inequality. Do the same thing for B check. So when that is done, this is what you get, okay? You see. Inequality involving the fourth order moment. Okay. You will also get the second order moments, but these we just showed that they are of this order, mu and mu minus squared. Then you will get W bar and W check squared, which in a previous lecture we showed they are of the order of mu and mu max squared. Okay. This is the driving term here, and this is that. Fine. Similar, right? The same ideas, okay? Same idea. Now take the limit. Take the limit. Okay. So this is not exactly the same gamma as before. I'm calling it gamma prime. I think there is here a small difference here, for example. Okay. But that doesn't matter. So if you take the limit, you will find that B bar is of the order of mu squared, B check is of the order of mu to the fourth, and from this you'll be able to compute that B itself to the fourth is of the order of mu squared, right? Then if you group this with A to the fourth, right? So B fourth will be of the order of mu squared, because B fourth is related, right, to this one, to this. Okay. Is there a, maybe a V is missing here? Is there a typo? No, this is B itself. Okay, this is B itself. I call the top part B bar and the bottom part B check. So that's B, okay. Anyway, so you get that B is of that order. And because Z is B minus A, from Jensen's inequality you have this, correct? And we conclude what we wanted to conclude. Of course, if Z is of the order of mu squared, remember that Z is related to W tilde I. Okay. This is the relation. W tilde is related to W bar and W check. And Z in this case, I define W bar and W check, I define as Z. The norm of that is mu squared, you get mu squared. Fine? Okay. So the arguments are similar to what we have done. I'm not going to go through the detailed proof, but I have the detailed proof here, right? So you write the recursions for B bar or B check, find bounds on the noises, just like we did before, and then use Jensen's inequality to that. Okay. So let's now go to first order stability. So that's the last part that I need to talk about. So now, what remains is to show that the first order moment on average is also stable and enters the region of the size of mu, right, for the long-term moment. Okay? Again, the argument is very similar. Actually, in this case, it would be simpler, because what was the recursion for the long-term model? It was a constant B, right, plus A2 transpose N SIE minus A2 transpose N B. Remember, this was the recursion for the long-term model. Now take expectation of both sides. We take expectation here. B is a constant, so the E can come inside here, right? S is 0 mean. So you end up with this recursion, correct? This recursion. Now this is simply a first order recursion driven by a constant term, right? B is stable, so the proving stability of the first order moment is much simpler for the long-term model than for the actual network, which is what we did last time. The entire lecture last time was to prove the result of this theorem for, most of the lecture last time, for the network. But for the long-term model, it's simple. Here, you see this recursion is stable. So where does this mean go to? Okay. So here it is. Okay. I could have done it in an easier way, but that's okay. I minus B inverse times that. Yeah. Right. Okay. I minus B inverse times that. Okay. The reason I'm transforming it to B bar is because I know the size of the entries of B bar. Okay, that's what I showed last time in the lemma. I showed you the size of the entries of I minus B bar inverse. Okay, so that's why what I'm doing here, I'm going to use the same similarity transformation, V epsilon transpose, okay, to transform this. So here it is. I already applied V epsilon transpose. Okay, so the B is replaced by V bar. Okay, and the term that's driving it, when you multiply by V epsilon transpose here, okay, this term here, by the way, has that form, right? 0 something, okay? Because of the definition of the limit point. Okay? So when I transform it, this is what I get. Okay? This is what I get. So now, what is the limit of this z? I minus b bar, inverse times 0 b check. And I know the size of the entries of I minus b bar inverse. That's why, okay, because I minus b bar inverse is what? Remind me. Do I have it here? Yes, 1 over, here it is. Right? I minus b bar inverse, I know that the entries are of this size. B check is that. So when you multiply these two, what do you get? 4 mu. Right? 4 mu. So this z here is of the order of mu. Right? So the norm of z is of the order of mu. But z, by definition, if you go to the recursion, I call this z, right? So the norm of z is of the order of mu. Okay. So this norm here is of the order of mu. Okay. And now I'm interested in this norm, right? At every agent. Okay. So well, at every agent, this norm is obviously smaller than the norm of the entire vector because it's part of it, right? And this entire vector is related to the transformed vector for a similarity transformation. Okay. The similarity transformation, and I can take it out, right? And this I just showed is only, right? Fine. So I established the long-term model for you, right? I derived a long-term model driven by a constant matrix, and then I showed that it is stable, first order, second order, fourth order moment stability. I showed that, and then I showed that the trajectory of this model is close to the trajectory of the original, right? And by how much? So I was very explicit about it. I didn't just throw away that extra term. I told you what the effect of that is. Next time, I'm going to use these results to derive the MSD performance for the network. Actually, that will take 2 lectures to do. Okay. It takes some effort, but it is doable. Okay. Now, before I continue, I just want to show you an example. Most of it, if you are only interested, for example, in studying mean square error networks, which means the individual costs are mean square error costs, expected value of d minus u gamma, for example, squared, right? Mean square error costs. Most of these derivations will simplify, will get simpler. Why? Because the Hessian matrix is a constant right away, right? The block diagonal H that will appear will not be the random H that we see in the general case, which we have to split into H and H tilde, and then we have to take care of that H tilde and show that if we throw it away, it doesn't cause too much trouble, right? You see, that's because we are studying the general case, right? We want to see how far we can go in the statements if your cost is general, because we want these results to apply to a range of problems, not just mean square error estimation, right? That's why we are saying these strategies that we have and variations that you can develop around them. You can use them to solve adaptation problems, learning problems, optimization problems, more generally over networks, right? It's because I would like to keep the analysis more general, I have to go to these arguments, right? And it is useful for you, right? Advanced graduate students that you see, right? How that you see these arguments at least once, right? So that you know the type of arguments that you need to develop when you study networks of this kind, right? Okay. Now, so that completes that. Now I would like to go back to the algorithms and use some of the results we have developed so far to compare them more closely. Some of this discussion you have already seen different forms of it before. Okay. Now I can add a little bit more and give you an analytical example. Remember that we have two classes of algorithms, right? We discussed these two classes of algorithms before, diffusion networks and consensus networks, right, over an agent. And I explained to you before that consensus iterations have an asymmetry in the way they run the recursion, right? And that asymmetry does not exist in diffusion networks. And that translates in a particular dynamics for the evolution of the Wave error vector, right? Okay, so let's look at that a little bit more closely. So for example, for any one of these algorithms, consensus, diffusion, or ATC or CTA, combine and adapt, or adapt and combine, what you do, you pick any two of the A's, you set them to the identity, and the other A you set it to some left stochastic matrix. That's a special case of the framework we have developed so far, right? Our results apply to the general case when you have multiple A's. That's possible, okay? And I even have some problems in your homework assignments where you study the case where the underlying topology for these A's need not be the same. These A's are combination policies, right? They are defined over a topology. On every link you put an entry, right? A. These different A's and the neighborhoods across these different A's, they can be different. Okay, this is something that you can study. Okay, you can do that analysis in your homework. Okay, but here I'm not doing that. Okay, so now if I write down the error recursion for the long-term model, because I just showed you that if you leave these networks working, first of all, if the step size is very small, we know from the last two lectures that, okay, if the step size is very small, okay, here we are going to violate some of these conditions, okay, that these networks behave in a stable manner. But now I want to look closer at this. Okay, I want to look closer at this. Okay. Now, I already did this example for the mean square error case. Okay. For the mean square error case, I have a detailed example where I showed you what this B is for consensus and diffusion. I even used a chronicle representation for that, and I told you that in one case, the coefficient matrix is the non-cooperative matrix times the left stochastic matrix. In the other case, this A appears as additive. And I explained what the ramification of that was. Remember that a left stochastic matrix multiplying the non-cooperative term will always be stable if that non-cooperative term is stable, no matter what the topology or what they is. Not true for consensus. Here I'm trying to do it more general, not just for mean square error costs, but for general costs. And the way I'm going to do that, I'm going to look at the evolution of the mean, and the evolution of the mean for the long-term model, okay? Well, the mean recursion, remember again, we had, we had an error model, WIE prime is B, WIE prime minus 1 plus A2 transpose MS, right? Plus or minus A2 transpose MB. So if you take the expectation of both sides, this term is going to disappear and you get this recursion, right? So this is how the mean evolves over time. Okay. What is the B? Well, the B, for the non-cooperative case, it will be I minus the diagonal matrix involving the Hessian matrices, right? H, that constant H, correct? Okay. So this is a block diagonal matrix involving the individual Hessian matrices, right? For diffusion, the B will be that non-cooperative B multiplied by the left stochastic matrix, either from the left or from the right, depending on whether you do the combination step before or after, right? For consensus, right? For consensus, the B will be the non-cooperative case, right? You can write it like that. Actually, for consensus, it is simply A transpose minus MH, which is what is written here. If you combine these two terms, that's what you get, right? So it is additive, not multiplicative. Okay. Now we already know, right? I already know. Okay. to make the non-cooperative solution stable. Pick step sizes, right, such that what would be the step size for agent K, for example? What bound does it need to satisfy for mean stability? Okay, here I'm talking about stability in the mean. Okay, what would be the condition on the step size? Mu K less than 2 over the spectral radius of the corresponding Hessian matrix, right? For this here to be stable, correct? Now, if this matrix is stable, we know from the properties of when I discussed reviewed matrix results here, lectures ago, I showed you, right? This was one of the results that we discussed, is that if you have a block diagonal Hermitian matrix, it has to be block diagonal Hermitian, right? The result was proven for that case. The block, diagonal, and these blocks are Hermitian. That's exactly the case of the non-cooperative B, correct? It is block diagonal, and on the diagonal, these blocks are Hermitian. Okay? So if you take a block diagonal Hermitian matrix and you multiply it from the left or from the right or both by left stochastic matrices, the spectral radius of this product never increases relative to D. Right? So what this means is that if D is stable, if the spectral radius of D is strictly less than 1, the spectral radius of this product will never be larger than 1. Right? So if D is stable, no matter what A1 and A2 you pick, this product is also stable. And that's exactly what you see here, right? Whether it is ATC or CTA, you are multiplying from one side by A, from the other side by the identity, right? These are left stochastic matrices. So if the non-cooperative solution is stable in the mean, the diffusion solution will always be stable in the mean, regardless of how you pick A, regardless of how you connect these agents together, right? Which is a very interesting, useful property to know. The same thing is not true for the consensus algorithm because of this additive nature, right? And I showed you an example before, I showed you an example again, okay? Because of this additive nature, A transpose minus MH, okay, if I minus MH is stable, you can't find A's that are valid left stochastic matrices that will make A transpose minus MH unstable. Okay? So this is one of the issues that come up because of the form of the update that you have, the asymmetry that you have in the consensus update. Okay? In one case it is additive, in the other case it's multiplicative. Okay? So I have an example. So just before I get into the example, here I'm motivating the result. This is the statement I just mentioned to you, that if x1 and x2 are left stochastic, that holds, you can make here each agent stable by doing that. Okay. So this slide is just repeating what I explained, okay? That these conditions will always hold. Okay. So let's take an example, a simple example here. Okay, a simple example. I have a network consisting of two agents. Okay, two agents. So this is an MSE network here. And the reason why I'm using this network is because I can do now the calculations in closed form. That's all. Okay? I can do the calculations in closed form. But the conclusions of the example are more general. They are more general. So let me see if I have a figure here. Should have a figure. This is the figure. I have two agents. Okay. Of course, this is a trivial network just because I want to do the calculations in closed form. Okay? So agent 1 is using A and 1 minus A, and agent B is using 2 is using B and 1 minus B. Okay? So for example, when 1 receives data D and U, it updates its W, gets an intermediate psi or phi. 2 does the same thing, gets its intermediate phi. Then they share their phis. Agent 1 is going to multiply the intermediate estimate of 2 by A, its estimate by 1 minus A, add them up, that becomes its next estimate. The same thing is being done by 2, and the process continues, right? Okay, this is for the diffusion implementation, okay? So here it is. I have two agents, okay? I'm going to assume that the covariance at agent 1 is given by this, at agent 2 is given by that. A multiple of variables. Why? Just to keep the calculation simple. I want to give you an analytical example where you can see that this is indeed the case. Okay? let's assume that the variances at the agents and the step sizes satisfy these conditions. Right? I can always do that because I'm free to choose the mu's. I'm going to choose a mu for 1 to satisfy that. Okay, very good. So the A's, the left stochastic matrix that's being used, remember A and B are right non-negative numbers between 0 and 1 because this is a convex combination. This is the A. Of course, if you would like A to be symmetric, for example, just choose B equals A, then it becomes symmetric, right? It becomes symmetric, right? So now that I know A, you can come back here. You see, what is B in the non-cooperative case? Right? It could be just sorry. Right? Minus something like this, mu1, sigma 1, mu2, sigma 2, I, right? Okay. So you know this, multiply by the A, I know the A, you get B, you get that B, right? So here it is. So I know for this example, what the matrix B will be in each case. Just plug back into the expressions, right? I know A, I know the non-cooperative B. Okay, so here it is. So this is just showing that this B is scalar, chronicle I, that scalar, okay, chronicle I, and so forth. So now, okay, so the first one is the non-cooperative B, the second one is the diffusion B, the third one is the consensus B. I'm just showing it for A, B, C, right? You can do it for C as well. Now, I already know, no matter how you choose A and B, that's an interesting matrix result, no matter how you choose the convex combination weights A and B, if this one is stable, right, just choose your mu1 to make sure it is stable, right? And similarly for mu2. So let's assume that that's the case for now. No matter how you choose A and B, this matrix will always be stable. Right? You already know how to prove it. Okay? It's difficult perhaps to see it from here, but from the property of the lemma we know. But this is not the case for this matrix. You see, for this matrix, right, the quantities appear differently. You see here it's additive here, it's multiplicative here. Right? So let's do some algebra. Okay? So let's assume that the step sizes are picked in this manner, which means the individual agents are stable, right? mu1 is less than 2 over sigma 1, mu2 is less than 2 over sigma 2, and additionally I'm requiring, this is an example, I'm just constructing an example, right? mu1 sigma 1 less than mu2 sigma 2 squared, okay? So both agents are stable, okay? Very good. Then I know that the diffusion, no matter how you choose A and B, will be stable. If you run it, it will converge. What about consensus? I want to show that there are choices for A and B that will make the consensus implementation unstable, right? So this is what I'm going to show. If your A and B are such that their sum is larger than this value, remember, I chose mu1 sigma 1 to be strictly less than 2. So 2 minus that is a positive number, right? It's a positive number. If this sum is larger than or equal to that positive number, any A and B that satisfy this condition will make your algorithm, the consensus implementation, unstable. One way to see that is as follows. If you go to the consensus matrix you have here, you have to do some algebra. How do you find, let's say M is 1, even if you want to keep it equal, you don't need to make it M1. What are the eigenvalues of this matrix? They are the pairwise products of 1 times the eigenvalues of this 2 by 2 matrix. How do you find the eigenvalues of the 2 by 2 matrix? Simple, right? You can do it because analytically. So we did that calculation. This is one of them, the smallest one. Okay? This is the smallest one. It is in terms of A and B and mu's and the sigmas and this tau, the expression for it is on the next page. Again, in terms of the A's and B's. Okay? This you can do analytically. It requires some algebra, right? Okay. Now, what's interesting is, okay, is that this tau you can rewrite it as you see in the second. What did I do there? So if you add these two terms, you have to expand this square to get exactly the first term. This is just algebra. But why did we write it in the second form? Because in the second form we had the sum of two non-negative terms. You see, this is one term which is non-negative, and this term is non-negative because I select mu1 sigma 1 squared to be smaller than, right? So tau is the sum of these two non-negative terms. So obviously tau is non-negative. So you have the square root of tau in the expression for lambda min. So this is real. Okay, real. Okay, so everything is real here. And tau is obviously, okay, so this is non-negative here, okay, non-negative. Then, okay, the lambda min, because if you go back here, you see lambda min, this is minus here, right? Minus. So lambda tau is larger than or equal to this term, correct? Because it is that term plus something non-negative. So it's larger than or equal, okay? So I can bound minus the square root of tau, okay, by the square root of this, minus the square root of that. Fine? It's just simple algebra. Okay? So here it is, the square root of that. So lambda min is upper bounded by that, because I replaced minus the square root of tau by a bound, okay? If you subtract these two, you will get this difference. But remember, I told you that A plus B satisfies this condition, right? This condition makes this difference less than or equal to -1. So you see here, I showed that there is a range of A and B that will make the smallest eigenvalue of the matrix less than or equal to -1. So therefore, it will make the consensus B unstable, right? So this is, okay, one conclusion. So this is an analytic example, okay? So you can do the calculations by hand. And then, of course, I showed you this simulation before. For this example, if you choose the numbers to satisfy the conditions I showed you, you are going to get this kind of behavior. Diffusion is going to converge. Here it is. It goes all the way down to about -50 dB. But consensus, that the mean behavior diverges in this case, okay? Which is a reflection of the argument I just showed you. But let me show you something more. Okay, so this is here, I'm just explaining the details of the simulation, the size of the vectors, okay, and the sizes of the step sizes and so forth, okay, and the variances that I used, okay. So I'm just giving you the numbers. Let me pursue this a little bit further. Let's pick a situation. Before I picked mu1 sigma 1 squared less than or equal to mu2 sigma 2 squared less than or equal to 2. So both individual nodes were stable. Any way you connect them and run diffusion, it remains stable. But even though the individuals are stable, I showed you consensus can become unstable. Let's now take this example. What's the difference now? One agent is stable, but the other is unstable. The individual nodes, one can solve the problem, the other cannot solve the problem, right? So I'm going to show you no matter how you connect them and run diffusion, run consensus, consensus will always be unstable. But diffusion can stabilize them, okay? So this one showing there are different aspects, okay? So because one of them is unstable, okay, this is what's going to happen, okay? If you go back to the consensus B and find again its minimum eigenvalue using the new condition I have, right? The new condition I have is this, okay? This is just algebra again, okay? Just algebra, you can follow it, okay? I can find a bound on the smallest eigenvalue of B. If you just carry out this algebra, you're going to find again that this smallest eigenvalue is always less than or equal to -1, no matter what A and B are. So the consensus network in this particular case will always be, if one of them is unstable, the consensus network in this example will remain unstable, no matter how you choose these convex combination coefficients A and B. Okay? What about diffusion? Okay. Well, now if you go to the diffusion B matrix and you find its eigenvalues, for this example, Okay. For this example, you are going to find this that the eigenvalues are given by this expression here. This is one of them, 0. So that one is stable. And this is the other one. Okay, this is the other one. All I need to show is that there is a choice for A and B that makes it stable, right? That's all I need to show. For consensus, there is no choice. But here, I just want to show that there is a choice. So I'm selecting the A to be symmetric, just to simplify the calculation. So assume B is 1 minus A. Okay. Then I will select the A to make this eigenvalue smaller than 1, right? Well, it's simple to find what condition A should satisfy to make that quantity there smaller than 1, right? Just solve for it. Well, remember that node 1 is stable, so the numerator here is definitely stable, right? And remember that I chose this quantity to be less than that quantity, so the denominator is also stable, right? Okay, sorry, positive, right? So this bound, this upper bound is positive. So there is an A, and therefore there is a B, right? There is a B, okay? So there is a range of values A and B for which the diffusion network can be considered. You have a question?
Yeah, so with that condition, the matrix A will become symmetric. I don't think that's.
So what was A? Sorry, what was A?
1 minus A, 1 minus A comma.
Maybe not symmetric, but that's the condition I would like to pick here in this example. Here. So I'm picking this thing here, I'm picking what? B to be 1 minus A, right?
To be symmetric.
So it will not be symmetric, it will be a rank 1 matrix. But still it is left stochastic, the columns are out. I just want to show that there is a case, right? There is a case, that's all. Okay? You understand? Okay, so that was the purpose of this lecture, okay, to motivate the long-term model, which I'm going to use in the next lecture, and to show you that indeed it's a good approximation for the actual model and tell you exactly by how much they differ and that it is stable, number one. And number two, to get a little bit deeper into this question of how does the performance of consensus and diffusion compare, and how does the asymmetry that you see in consensus influence behavior. So I showed you here that if the agents are stable, no matter how you connect them, the diffusion network will continue to be unstable. But this is not necessarily the case for diffusion and for consensus networks. Okay? And then I gave you another example where if the individual agents are not necessarily all of them stable, diffusion can stabilize them because you always reduce the spectral radius of B, but that's not the case with consensus. Right? That's what this is. Okay? Good. Yes?
If we have a complex, like complicated objective function whose Hessian matrix is not block diagonal, how will we find the minimum mu that we need to make the network stable?
You are confusing two things. This Hessian matrix that appears in the dynamics for the error recursion is always block diagonal no matter how complicated your function looks like, right? Because it contains the Hessians here, right? These are the Hessians of the individual costs, which you take, of course, evaluated at the proper arguments, right? If it is the constant H, this is at omega star. If it is the random H, it's at the proper argument. Whatever your J sub K is, you find its Hessian matrix. That's a block matrix. It's m by m in the real case to m by 2m in the complex case. You put them here on the block diagonal. So this calligraphic H will always be block diagonal. Okay?
But the H's may not be Hermitian.
No, the Hessian is always Hermitian, right?
Not necessarily.
Block.
Yeah, no, the Hessian, this H itself is not necessarily block diagonal. That's why we have to extend. Remember the E, this E came from that, right? The reason why we are carrying this E is because these H's may not be block diagonal. If these H's were block diagonal, your recursions collapse. You don't need the E. You can work only with one part of that extended time.
So
maybe your question is.
My question is, how do we find the mu? So for this case, we were able to find, right, mu should be less than or equal to 2 over the rho of H.
Yes.
But if for this case, how would we find the mu?
Which case?
H is not diagonal. It's general H.
Yeah, for general.
It's no, that condition
Oh, this is what it means for the networks.
here, right?
Yeah.
This thing here.
This example is for mean square networks.
But this always holds.
You're talking about this condition?
Yes.
Well, this condition is in terms of the spectral radius of the individual Hessian matrices, right? The individual Hessian matrices. These are the constant matrices, right? If you have J sub k, this is the HK that comes from it. If you find its spectral radius, it will give you this pound.
So this always holds, irrespective of whether it's a mean square error network or whether it's a...
Yes, what happens in the mean square error case is that H sub k becomes the covariance matrix, right?
Right.
That's all. But in general, it is the Hessian matrix that will appear there. Regardless of what it is, you have to find its spectral radius to the, and this bound only guarantees mean stability, right? So here I just, this example only deals with stability in